once it's fixed onto the stage, we can change the stage angle, and so that's the angle at which we're looking at the feathers. But also the advantage of the goniometer is that we can change the angle of both the spectrophotometer and the angle of the light source.
Interesting.
And so the idea here is that if we change the angle of the spectrophotometer and the angle of the light at the same time, we're getting specular reflectance, so that's the equivalent of shining light on a mirror. So that's a light that bounces directly back at you. And if we change the angle between the spectrophotometer and the light by moving only one of the arms, now we're getting diffuse reflectance, which is not that nice shiny color. It's more what we see from the edges.
Interesting.
So
all of this is reflected light as opposed to transmitted?
Absolutely, yeah. In this case, we're only measuring reflectance. And the idea is to be able to look at this angle resolved spectral data and try to match it to predictive models of the nanostructure of the feather. So we also take small barbules, we slice them with an ultramicrotome, look at them all under transmission electron microscope, and then we try to model the structures that are found inside the feather to match the colors that we're actually measuring.
Marvelous. Actually, we had Rich Pram come and give a talk last term.
Exactly.
That was a lot of fun.
Yeah.
Very interesting. So what's the specific research question with this feather?
In this case, what's really neat about the hoopoe and one of the other feathers I was measuring off of a turkey today is that they have hollow melanosomes. So a lot of birds have solid melanosomes. They're usually rod-shaped. These are hollow, and it offers quite a bit more reflectance normally, so a bit brighter in the feather. But also it seems as though with a change in angle geometry, we're getting not only a change in color, but sometimes a complete change in geometry. And so we get a peak not only shifting, but it jumps from one hue to another. And so this is what we're looking at right now. We've identified a few species in which that seems to be the case. So now we're modeling these colors. This is in a collaboration with a PhD candidate at the University of Akron. His name is Chad Eliason. He's working with Matt Shockey. So we're modeling these colors.
Thank you very much. So if we hit the lights, we can see the spectrum on the screen.
And so this is a relatively low reflecting feather, so not a lot of brightness. But with the change in angle, we can see that it actually reduces in brightness. And in this case, there's not much of a change in the peak, so basically there's no change in the hue. In some species, the change in the hue is quite drastic with the change in angle. Often enough that has to do more with the ultrastructure of the feather. So if the ultrastructure is curved, then we won't get these, we'll get very little change in the color. If the feather is flat, the barbule is flat, then normally we'll get much greater change in the hue of the feather.
Okay, well thank you very much. That's most
no
informative.
problem.